On partial differential equations, we'll be looking specifically on the wave equation. There are many other partial differential equations like the heat equation and the Laplace equation, which is used mainly to prove harmonic equations or functions, whether they are harmonic or not. Um, but here we'll be dealing mainly with the solution and the implications of boundary conditions and initial conditions on the wave equation for a vibrating stretched string. So some of the learning outcomes that I expected is that we'll be able to set up as well as interpret a model governed by a one-dimensional wave equation for a vibrating stretched string. Also, to be able to verify that a particular solution or a particular function that has been given is a solution to that specified wave equation. Thirdly, be able to solve the wave equation using the method of separation of variables. Also be able to discuss the characteristics of the solution for a wave equation. But before we can be able to get into all of that, we need to be able to have pre-knowledge of the terminology pertaining differential equations. Also, which is more important, the knowledge on partial differentiation. And this one will be forming the last part of our solution, where we'll need the knowledge and skills of basic integration as well as integration by parts. Also, even on that latter part, we need to be able to use or to know the Fourier series expansion of a function. In particular, most of the problems we're dealing with will be using the sine series, which we take directly from the Fourier series expansion. Before we can go into all of that, firstly, let's introduce the general formula for a wave equation. It's given as the second derivative of u with respect to x equal to 1 over c squared multiplied by the second derivative of u with respect to time, where our u is representing the displacement of the wave. Remember, we're looking at a vibrating stretched string, so we're looking at the waves. So therefore, we have to know the displacement of each wave, also the speed, which is given by c, the speed of the wave. Why is that? Because we need to know what happens at the edges or at the ends of that stretched vibrating string. Is it fixed on both ends? Is it fixed on one end? Does the length of the string change over time? Does the displacement change? Does the speed or the velocity of the stretched vibrating string change over time? And then how then do we write the initial conditions and boundary conditions depending on what happens at the end that is at the start and at the end of that particular string. Now, one other thing that we need to note, sometimes this wave equation is written as c squared multiplied by d squared u over dx squared equal to d squared u over dt squared. So let's not get confused. C squared might be multiplied to the second derivative of u with respect to x on some equations or some problems that we may encounter. One other thing, we also, because of the second derivative with respect to t, we must have two initial conditions. And the second derivative with respect to x says that we must have two boundary conditions. Note that initial conditions always refer to t, and boundary conditions always refer to x. So the string must have a length. So our string always starts from x equal to 0 to x equal to L, where L will be specified depending on that particular length of string. So our boundaries, x starts from 0 to x equal to L. Initial conditions, I hope we still remember initial, it means t must be equal to 0. So what happens at the start? Do we have initial displacement? Do we have initial velocity at the start or at the beginning of the string? Now let's go to the interpretation of the boundary conditions and initial conditions and how we can write them in mathematical format. Number one, when the vibrating string, note again, of length L has its ends fixed, then note we're not talking initial conditions now, we're talking boundary conditions because we're looking at the length of the string. What happens at the beginning and what happens at the end of the string. So now we're told that the ends are fixed, meaning that will only have u of 0t equal to 0 for the left end, and for the right end, that means at the far end of the string, we'll have x equal to L. So that means we'll have u of LT equal to 0. Now please note that when we write the variables for u, in this particular notation we're using here, x is the first variable and t is the last variable. In other textbooks, you'll discover that they start with t and end with x. So for our notation, please remember u has variables x as the first one and t as the second one. So the only change here that we see in the variables are the x values, x equal to 0 and x equal to L. Please remember, no derivatives when the string's ends are fixed. Now let's go to when one end is fixed and the other one is allowed to change or vary as time changes. So here we have the left end is fixed. So we know from number one that will have u of 0t equal to 0 because the left end is fixed. Let's say maybe the string is attached to a wall on the left end, but the right end side is free to change length and vary. It means when it changes length, it means that we then have a function of time, not 0 on the right-hand side of the second boundary condition, because the length or there is a displacement that is happening on the right-hand side. So that means the final displacement of the string changes with time. Remember, we had said U of xt stands for displacement. So there is no displacement on the left side because the string is fixed, but on the side where the string is not attached, then the final displacement changes and is written as a function of time. So note that it could be f of t, or it just could be 1 or 2. It could be constants. So it might not necessarily just be a function of time, but we wrote here f of t, noting that f of t can be a constant, can be a polynomial, can be an exponential function, or can be a trig function. So we can give you anything on the right-hand side of the second boundary condition. But just note that the second boundary condition, when it is not equal to 0, it means that the right end varies with time. That means the final displacement changes on the end where x is equal to L. Then we go to the third one. What if then we have disturbed the string in its initial position of equilibrium initially? So that means now there is a movement on the initial part. That means when x is equal to 0, or should I say at time t is equal to 0, something happened. So we have initial displacement not equal to 0 because initially there is movement. We look at the string when there is movement at the initial position. I'm hoping that we're noticing that once the string has been disturbed at the initial position of equilibrium, then it means on the right hand side we have f of x for the first initial condition. Note, because now we are talking about initial position, so t is equal to 0. Now we'll have u of x0 equal to f of x. Now we're not dealing with boundary conditions as number 1 and number 2. We're dealing with initial conditions because we're looking at what happens at the initial or at the start of this whole process that we're looking at. Then it says, afterwards, note the string was disturbed initially, and then thereafter it was released to vibrate freely. When it's vibrating freely, now we're not talking displacement, we're talking velocity. So that means we have the initial velocity to be equal to 0. Initial velocity, we need to remember if displacement is u, then velocity is du over dt. That is why we have u subscript t representing du over dt when time t is equal to 0. So it means initially we have disturbance, so that means we do have initial displacement equal to a particular function that will be given to us. But that function, note, is a function of x. And then releasing it freely to vibrate, then we have initial displacement, initial velocity, which is du over dt at time t is equal to 0. And we know that it will be equal to 0. because it has not been given. Number 4, we just want you to look at if we're saying the initial displacement is equal to 0, or in high school we used to say that initially the object was at rest. So that means there is no initial displacement. So we have u of x0 is equal to 0. Initially, when there is no displacement at t equal to 0, then we have u of x0 equal to 0. And then when you set the string in motion at time t is equal to 0, then we must consider the initial velocity. Once there is motion at the start of the whole process, then that means there must be initial velocity, and our initial velocity will be a function of x. Then the last one, if now we say that we have the left end is free and only the right end has been attached, then we are saying left end free, it means there is a change, all right, in displacement, and it's also a function. And also on the right hand side, we have a displacement that, sorry, the velocity that is equal to 0, because the right end is attached, so that means there is no final velocity. Now let's go to the solutions of these problems. Firstly, we have to notice one thing. We'll always give you the governing formula for the wave equation. You'll always be given. And the value for c, which is the speed of the wave, will always be given. Also, you might or you may be given the general formula. The general formula for the solution of that wave equation. Now we need to note this. The method of separation of variables is a very long method because u is a function of x and t. Then we separate the variables and we say u of x and t is equal to x of x multiplied by t of t. Then we solve. That is a huge process, but for your syllabus, we start at the step where you've discovered what the general formula is. Note, it becomes a general formula because you still have constants a, b, c, and d. Now note, we've separated the variables here. The first part is on the right hand side, it's a function of x. Second part, functions of t. Note c is part of the argument of the second portion, but it is not there in the first portion. So when we start to solve whatever we are asked to do, we have to substitute the value of c in for the second bracket. Also, we will always be given the conditions. Remember, we had said you'll always be given 2 initial conditions and 2 boundary conditions for any wave equation. Now, the first thing that we've been asked to do, identify the initial conditions. Remember, when we say initial conditions, it means time t must be equal to 0. Then we say that's an initial condition. So it means the third condition and the fourth condition are the ones that are initial conditions, because in both the value for t is equal to 0. We are not mindful of what is happening on the right hand side. No, we are just looking at the value for t or the value for x. Are those the ones that are changing? And for initial conditions, t must always be equal to 0. Then we're asked in B to identify the boundary conditions. Boundary conditions, it means the value for x must be the one that changes. So now x equal to 0, and then x is equal to L, and our L has been given here, and they are both equal to 0. So it means u of 0t is equal to 0, u of 4t is equal to 0 as well. Those are our boundary conditions. Why? The value for x changes. We're starting on the left end when x is equal to 0, and on the right hand when x is equal to 4. Now, the third question asks, are the ends of the string fixed? According to the first condition that we talked about, immediately we have the displacement at the start of the string equal to 0, and the displacement at the end of the string is also equal to 0. It means that the string ends are fixed. Number 4, we are asked, which is D, what is the length of the string? The second boundary condition gives us the length of the string. The length of the string is 4. If E was asked, what is the speed of this wave, would know the speed of this wave is 2, because we've been given that the value for c is equal to 2. Also, this is worth noting, du over dt at time t is equal to 0 is equal to 0 represents the fact that the initial velocity of the string is equal to 0. So that means the string was initially at rest. The last initial condition is we're being told that there is displacement at the afterwards. So initial velocity is 0, but then you have a displacement afterwards that has been given. So we need to go back and check which ones, these two initial conditions, what are they based on? Are they based on 3, 4, or 5 of those conditions that we had looked into? Number 2, here we have been given a mathematical model, and we are told the ends of this vibrating string are fixed. Now, the wave equation has been given to us. Remember, I had said to you that usually it's d squared u over dx squared equal to 1 over c squared d squared u over dt squared, or we can just multiply c squared to the second derivative with respect to x. That's exactly what has happened here. C now is multiplying the second derivative with respect to x. It's the same thing. Our value for c, note it's not 4, but it is 2. Remember, it's 1 over c squared. So 4 is c squared. So that means the speed of this wave is 2. Now we're given 2 initial conditions. And guess what? We've been given 4 conditions. What we see written there mathematically are the initial conditions, because the value for t is equal to 0. in both. But then the statement tells us the boundary conditions, that the boundary conditions have been given. The string is fixed at both ends. Now let's go to answer the questions. Firstly, we are asked, describe in your own words the physical meaning of the condition u of x0 equal to 0. And I'd already specified that the string was initially at rest, or the initial displacement of the string is 0. They both mean the same thing. Remember, u of xt is the displacement. So initial displacement of the string is equal to 0, or the string was initially at rest. Then B, we're supposed to write down the boundary conditions of the problem so that we complete the model when the length of the string is given. Note that in this whole problem, the length of the string is not there. So now we have the boundary conditions of the problem based on the fact that our string is fixed. So we've written the mathematical, so we've completed the mathematical model because we've written down the mathematical expression of the ends that are fixed. Now let's go to the next question. We are asked here, if the given function u of xt is a solution for the given wave equation. So the first thing that we do, we have to remember what was the given equation, wave equation. The given wave equation had on the left hand side the second derivative of u with respect to t. On the right hand side it had 4 times d squared u over dx squared. So it means we have to find the first derivative, all the first derivatives, and all the second derivatives with respect to both u and t, both x and t. So let's start with finding du over dt. Note that with partial differentiation, our functions usually are a function of both x and t. So we need to make sure that when we are differentiating with respect to t, we treat the variable x as a constant. So out of this function, 1 over 4 sine 4t sine 2x, you need to make sure that sine 2x is treated as a constant because you are differentiating here with respect to t. Hence, I wrote here 1 over 4 because it's a constant. We take it out anyway. And then in brackets, I gave you the derivative of sine 4t, which is 4 cos 4t. And then took down sine 2x as it is because it's not affected because we're differentiating with respect to t. And then simplifying, we got cos 4t sine 2x. Please remember that every time you are doing partial differentiation, you need to always keep in mind which variable are you using. partial differentiation, you need to be mindful of which variable you are using. So now here we are using t, so we have to make sure that we hold x as a constant. Now let's go to the second derivative, because remember that formula that we're dealing with requires us to have an answer for the second derivative with respect to t. So again, 2x sine 2x does not change. We find the derivative of cos 40. We know the derivative of cos is negative sine, and then the argument of cos was 40, so we have to multiply that by the derivative of the argument. Hence, we say that the answer is negative 4 sine 40 sine 2x. Then we go to the derivative of u with respect to x. Now, because we are using x variable for our differentiation, that means t is held constant. So we take out 1 over 4 and sine 40 and only differentiate sine 2x. So we'll have 2 cos 2x, and then we simplify our expression, giving us 1 over 2 sine 40 cos 2x. Once again, we need to remember that on the right-hand side, we have the second derivative, so that means we have to differentiate again. So we have half sine 40 multiplied by the derivative of cos 2x, which gives us negative 2 sine 2x. If you simplify that, 2 and 2 will cancel. It means we'll have negative sine 40 sine 2x. That is why for the right hand side, we substituted negative sine 40 sine 2x. And note the right hand side was being multiplied by 4, so that we get an answer for the right hand side. And then the left hand side, we had simplified it from up there, we write it as it is. And then we check whether the left hand side is equal to the right hand side. And then in this case, the left hand side and the right hand side give us the same answer. So therefore, we have to conclude, because remember, we were asked a question, is that function a solution? So we have to answer the question, yes, the given function is a solution to the given wave equation. Please note that you need to recall those partial derivatives, differentiating with respect to u and with respect to t and with respect to x, and going for the second derivative, and also go back to the original formula. Left hand side, simplify it on its own, get an answer. Right hand side, simplify it on its own, get an answer, and check whether your left hand side and the right hand side are equal. That's how we check whether a given function is a solution or not of a particular given equation. Now we go to D. The same function that has been given to us that we used in C. Now we are asked if it satisfies the mathematical model. Remember, in order for us to complete the mathematical model in B, we had to make sure that we have two boundary conditions and the two initial conditions that were given to us. So now we have 4 conditions. The mathematical model will be complete if we have all those 4 conditions. So now, here we know that in C, this function is a solution, but then does it satisfy the model? which means does it satisfy all the conditions? Does it satisfy the boundary conditions? Does it satisfy the initial conditions as they are? Now, what we do, we go for each condition and check whether that solution satisfies it. The first one that we were given, which is the first initial condition that was given, that came with the problem, was ux0 is equal to 0. Wherever there is t in u, we substitute 0. So hence I have there sine 4 times 0, sine 2x, multiplied by 1 over 4, and we got the answer to be 0. And that initial condition had said when we substitute t is equal to 0 into our u, we must get a 0. Really, the first initial condition has been satisfied. Guess what? Even when you substitute into the boundary conditions, remember the boundary condition, when you substitute in x is equal to 0, it must give you a 0. X equal to L. Unfortunately, the length of the string has not been given. So now we're not using the boundary conditions, we're using the initial conditions, because both initial conditions do not have the value for L. If the value for L was given to us, then we'll substitute all 4 conditions and check. Now we are going only with the initial conditions. Ut of x0. I hope you still remember this is the initial velocity. That means du over dt must be equal to sine x into 1 plus cos x. We are trying to check that. That is why I've got a semicolon there. We are trying to check that. So whatever we do, we must not equate it to that. We must try and check whether we're going to get that answer. So the first thing we do, find the derivative of u with respect to t. Our u is given, so we have 1 over 4 into 4 cos 4t sine 2x. So our answer is cos 4t sine 2x for the derivative. And then once you've got the derivative, now we are trying to find what it will be equal to when t is equal to 0. So wherever there is t, we substitute 0. Hence, we've got cos 4 times 0 sine 2x. So we've got cos 0 sine 2x, and we know cos 0 is equal to 1. You can check that from your calculators, and that gives us sine 2x. According to the identities, trig identities, this is just equal to 2 sine x cos x. Now, the answer we are getting, 2 sine x cos x, is not the same as sine x into 1 plus cos x, because sine x into 1 plus cos x, if you remove the bracket on the left hand side, you'll have sine x plus sine x cos x. You don't have 2 sine x cos x. Therefore, this function does not satisfy the mathematical model. I'm hoping that we all understood this. To check whether a given function satisfies the mathematical model, we need to substitute the conditions, or to check whether that function satisfies the conditions that have been given for that particular problem. Now let's go to the next question. Here now we are solving the problem. Once again, every time we ask you to solve for a wave equation for your syllabus, will give you the general solution. will always give you the general solution. A general solution fit for that particular problem. And because of the constants in the general formula, you are asked to find a unique solution, or what we know as a particular solution. Note also in the general solution, the value for C is equal to 1. How do I know that? In the second bracket, the argument of sine and cos usually is omega CT. Omega CT. And looking at the formula for our wave of this vibrating string, stretched vibrating string, the value for C definitely is equal to 1. Hence, you have omega t as the argument in the second bracket. Then you have been given also, I'm hoping that you're noticing, the length of the string has been given. X is between 0 and 1. So that means the length of the string is 1 unit, directly from the given interval for X. And also you've given that t is greater than 0, because we know time must be positive. Time cannot be negative. Also, we've been given 2 initial conditions and 2 boundary conditions. I'm hoping that you're noticing that the string is fixed at both ends. Then, the first thing to solve this problem, first thing we do is to substitute the first boundary condition. Hence, I've written here BC1. Taking the first boundary condition as it is, u of 0t must be equal to 0. And then find u of 0t. When you say u of 0t, that means you're saying the value for x is the one that is equal to 0. So it's x equal to 0. In the formula, substitute wherever there is x, substitute 0. And you can see that the second bracket has not been touched at all or affected by the value of x, because the second bracket does not have x. We go back to the first bracket. Cos of 0 we know is 1. Sine of 0 we know is 0. So in the first bracket, you'll only have a times 1 only after simplification, and then you have still the second bracket. Now, one other thing that we need to stress is that the general solution of the wave equation cannot be equal to 0. Cannot be equal to 0. So if we have now this situation, 0 is equal to a into c cos omega t plus d sine omega t as the second bracket. We remember from high school, it would mean that a is equal to 0, as well as the second bracket is equal to 0. And if we say the second bracket is equal to 0, and we go back to u to substitute it, u will become 0. And we cannot have that, because u cannot become 0. So we cannot take that whole bracket and say is equal to 0. It's safe then to say it's only a that must be equal to 0. Because when you substitute a into the general solution, when a is 0, the whole function u will not become 0. It's only the first term in the first bracket that will be equal to 0. So all in all, you will be having your u becoming b sine omega x into the second bracket. Now, one other thing, every time you solve for a constant, you need to update u, because we are trying to solve for those constants. So every time you get the value for a constant, substitute it in and give us an updated formula for u, because the updated formula for u will impact the next step. Remember here, a is equal to 0. We still have to solve for b, c, and d. So it's better for us to simplify our u by substituting the value for a in, so that by the time we go and substitute or use the other conditions given, we have a simplified version of u. Now let's go to the next step. We've used the first boundary condition. Now we're going to use the second boundary condition. BC2, I've written it as it is, that u of 1t is given to be equal to 0. Our u has been updated. Remember, we had b sine omega x into the bracket that has got c cos omega t plus d sine omega t. So u1 of t, wherever there is x, we substituted 1. So that means you end up with b sine omega only in the first bracket. And then the second bracket remains the same. No change in the second bracket. Once again, we know that we have 0 equal to b sine omega, and we've got the bracket c cos omega t plus d sine omega t. Now you have to decide what would be equal to 0. What would be equal to 0? Substituting now the second initial condition, which is du over dt when t is equal to 0 equal to 1. Note also, in order for us to solve these problems, it's easier for us to substitute the last initial condition that does not have 0 on the right hand side last, so that we get the last constant. But in order for us to do this, the first thing we need to do is to find the derivative of u. So we differentiate u with respect to t. And I'm hoping you're noticing that we'll only differentiate sine n pi t. And it gives us n pi cos n pi t. And then thereafter, we substitute the value for t equal to 0. And note that that whole derivative must be equal to 1. So wherever there is t, we substitute 0. Hence, we have the cos 0. And then we'll be left with 1 equal to that summation of bn n pi sine n pi x. Then we use our knowledge of the sine series. Remember, that's a sine series. But we have to find the Fourier sine constant using the sine series formula, which says the Fourier constant will always be equal to 2 divided by L multiplied by the integral of the function that is on the left hand side, which is f of x, multiplied by that sine function that you had in the sine notation, which is sine n pi x. We integrate with respect to x between 0 and L. So it's important that you know what is the length of this string we're talking about. Now note this. Because of the presence of n pi under the summation sign, we have to have bn equal to 1 over that n pi. Hence, we have 1 over n pi multiplied by 2 over L times that integral. Then we integrate. We need to remember the integral of sine n pi x is negative cos n pi x divided by n pi, which is the derivative of the argument of sine. And then we are integrating between 0 and 1 because our L is 1. Once again, we need to recall when we substitute the limits, we start with the upper limit first, followed by the substitution of the lower limit. But when you substitute the upper limit, you go directly wherever there is x, substitute 1. But when you get to the lower limit, we have to subtract the substitution of the lower limit. I'm hoping you can be able to confirm that when we have cos 0 here, this will become 1 over n pi. 1 times 2 gives us 2. 1 times n pi gives us n pi times n pi gives us n pi all squared. Hence, we have negative 2 over n pi all squared equal to into cos n pi minus 1. Now, one other thing that we need to take care of. Cos n pi, we had said sine n pi is always equal to 0. But cos n pi will always be equal to negative 1 all to the power n. You can check your calculator. When n is 1, you get -1. Cos of pi is also -1. When n is 2, you'll get cos 2 pi. Cos 2 pi is 1. Even on this side, -1 all to the power 2 is 1. So cos n pi and -1 all to the power n are exactly the same thing. So we found our formula for Bn to be in that format. Then we go to our u. Substitute directly the formula for Bn so that our unique solution for that problem is in that format. Note you still have that sin n pi x and that sin n pi t there. All you did was to substitute the formula for Bn. That's all. That's the end of this problem. Now let's quickly go through the second problem. Number 2. Once again, we'll be given a general formula for our one-dimensional wave equation, and we've been given conditions. And note there are 4 conditions, 2 initial conditions and 2 boundary conditions. Now note the difference. In our previous number 1 problem, our u of x0 was equal to 0. And we had du over dt at t equal to 0 equal to 1. Note now the difference. Our u of x0, that means the initial displacement, has been given. So that means this string was initially disturbed. And then we have the initial velocity being equal to 0. Also, the length of the string, note that it is pi, given by the second boundary condition. The string is fixed at both ends. Now, the first question asks, what is the initial displacement? Looking at the initial displacement at x equal to 0.5, looking at the conditions that we are given, the one that gives us the initial displacement, that means u of x0 is given by that formula, x over 4 into 1 minus x. Substitute 0.5 in there, and then you give us the formula, your final answer. You need to remember what is represented by the initial boundary condition and the last boundary condition, initial condition 1, which gives us the initial displacement, or which one that gives us the initial velocity. You must remember, initial displacement is u when t is equal to 0. Initial velocity is u when t is the du over dt when t is equal to 0. You must remember all those things. Now, here we go to B. C has been given to be equal to 1 in our wave equation, and we've been given that already we have a general solution of that format. I'm hoping that you're noticing which step is that. It is after we've substituted the first boundary condition and the second boundary condition. So both our boundary conditions have been substituted, and then we get that u. Immediately we have a summation sign. That means the boundary conditions have already been substituted. Now we need to make a choice. Which initial condition are we going to start with based on what has been asked? We are being asked to find the value for an. An is the coefficient for cos n pi. How do we get an? when we have already a formula for u after substituting both boundary conditions. We need to check what will work better for us. Are we going to differentiate u and equate it to 0? Or are we just going to substitute u of x0 as it is? Which one is going to work better for us? Now you need to think. In order for you to get an, it means we have to eliminate the term that has got bn. How do you eliminate the term that has got bn? Is when t is equal to 0, because we know sine 0 is equal to 0. That will eliminate the second term, which has got bn, and allow us to work with the first term and then be able to get our an. So it means between the two initial conditions given, we need to be able to check which one will work better by direct substitution of the value for t so that we eliminate bn. That means we can only use the first initial condition because that's the only one that will help us to get an by direct substituting t equal to 0 and eliminating bn. Let's look now at the solution that has been given. Also note that if we had decided, okay, let's choose the initial condition that is equated to 0, du over dt when t is equal to 0. Once you differentiate cos, it becomes negative sine. And when t is equal to 0, that eliminates the first term. I'm hoping you're with me. Once we differentiate u with respect to t, I'm just differentiating the first term. Cos becomes negative sine. And when you substitute t into the argument of sine, it eliminates the first term because we know sine 0 becomes 0. So we can only use the second one, which has got a derivative, when we want to solve for bn. Why am I saying though? So the derivative of sine we know is cos, and cos 0 is what? Is 1. It means we will be able to find bn when we use the second initial condition that has got a derivative. So it is very important to check which constant are you asked to solve for. If they specify solve this constant, like in this case an, in order for us to solve for an, bn must be eliminated. And the only way to eliminate bn is by just substituting t is equal to 0 as it is, and then bn will be 0. Actually, the whole term that has got bn will become 0, and we'll be able to solve for an because we know cos 0 will give us 1. Now let's take a look at what has happened in the solution for an. I've rewritten there the formula for u, for is. And then again, as I had mentioned before, we substitute the first initial condition because we've been asked to find an. And in order for us to find an, we have to eliminate the term that has got bn. And the best way to do that, direct substitution. So it means we have to use the initial condition that does not involve differentiation. So we know that u of x0 is equal to that function of x on the right hand side. So directly on u, we find u of x0, we substitute in. When x is equal to 0, we'll have cos 0 there. And we'll have sine 0 in the second term. Sine 0 times bn will become 0. So in that whole bracket, you'll be left with the first term that has got an only, because cos 0 is 1. Hence, we have an here, multiplied by that sine function, which is sine n pi x. So we have a summation of an sine n pi x equal to the right-hand side of that initial condition. And we know that our length of the rod is 1, because x has been given to be between 0 and 1. Immediately, you have a non-zero term on the right-hand side, and you have a sine series on the other side. It means we have to use the Fourier sine series formula, which we used when we substituted the second initial condition in the last problem. 2 over L times the integral from 0 to L of the function that we have on the right-hand side. Remember, in the last problem, we had 1. Here, it's not 1. We have to use x over 4 into 1 minus x multiplied by that sine n pi x that you had there that was multiplying an under the summation series. It must come under the integral sign. And we're integrating with respect to x. The challenge we have here is that we have two functions of x under the integral sign. Let's first substitute the value for L, which is 1. So that means we have 2 over 4, as I've simplified it on the last term. Under the integral sign, we multiply in our x. So we have x minus x squared inside the bracket, and then we have that sine n pi x dx. Now here comes the integration by parts. Remember, you take the simplest formula and be the one that you differentiate, and the complex one, it be the one that you integrate, so that when you do your differentiation of that first term, it must give you a 0 at the end. Also remember the signs. It's the plus sign first, minus sign second, plus sign. So you're alternating the signs. So I wrote down exactly the first row. You write x minus x squared, the functions that were given under the integral sign. Note that I don't have that 2 over 4. That 2 over 4, you'll see how it's going to come in. And then we've got sine n pi x under the integration. So here you've got u and dv according to the formula for integration by parts. So we differentiate x minus x squared, it gives us 1 minus 2x. You differentiate again, you get negative 2. You differentiate again, in the last row you get a 0. Note it's plus, minus, plus, minus. Then you come to the integral sign side. So you've got sine n pi x, you integrate it, it gives you negative cos n pi x over n pi. You integrate cos n pi x, it gives you positive sine n pi x over n pi, but you multiply it by that negative over n pi, and it gives you sine n pi x over n pi all squared. Then you integrate again, because you need to get to the last row that has got a 0. Integral of sine n pi x, we know it's negative cos n pi x over n pi. That's why we have a negative times a negative. The last term becomes positive. And then we have cos n pi x over n pi all to the power 3. Then we go back. We need to substitute. In place of the integral sign, we have to substitute what we got for an. Here is our an. The 2 over 4 has simplified to 1 over 2, and you're we have to make sure that you put that bracket in, because all the terms you're going to write down must be multiplied by that half. Now we go back to our table. Plus sign multiplies x minus x squared, and then note how we do the multiplication. It's x minus x squared multiplied by the second row answer in your integration. The second row answer for differentiation multiplies the third answer for integration. The third answer in differentiation multiplies the fourth answer in integration. You put those terms, don't forget the signs. It's a plus times that, it's a minus times the second one, it's a plus times the third one, and it's a minus times the fourth one. So now let's do this. As you can see, it was a negative on integration times a positive. So the answer must definitely be negative. Hence, you have that first term as it is. And then we go to the second term. We had a negative and a negative. So that gives us a positive. That is why you have a positive sign there. And then for the last term, you have a plus times a minus there times a plus there. So the answer should be a negative. And then we simplify. What do we know? We have the limits of integration, 0 and 1. Substituting the upper limit minus the substitution of the lower limit. Please confirm that you will get that answer. Remembering, sin n pi is equal to 0. Cos n pi is negative 1 all to the power n. Upper limit substitution minus the lower limit substitution. Simplify and check whether you'll get the same answer. Let's go to the last one for this problem. C. Now it says we must derive an expression for Bn, which will be the last constant. So what did I do? Because we already have an answer for An, substituted it. That's why we have that formula there. And then the last initial condition that we are left with is the one where we differentiate u with respect to t and substitute t equal to 0 and equate all of that to 0. Then it means that we have to first find the derivative of our u with respect to t. So that means you only differentiate cos n pi t and sin n pi t. Hence, I've got those answers there. Please check if my differentiation is correct. And then thereafter equate all of that to 0 as you substitute the value for t to be equal to 0. So wherever there is t, substitute 0 in. That's why I've got sine 0 there and I've got cos 0 there. Remember, we still have that sine n pi x on the outside. Then it's simplified to this step. Sine 0 is equal to 0, cos 0 equal to 1. I got only n pi multiplied by bn times sine n pi x equal to 0. Note that sine n pi x cannot be equal to 0. Note, there's our formula. Sine n pi x multiplies everything. So we cannot let it be equal to 0 because our u will become 0. So it means it's only the constant bn that will be equal to 0. That is why we have here bn equal to 0. and then we substitute into our u, and therefore that is the final formula for u, which is our final particular solution for our wave equation for this problem. Now let's take a look at an exercise that I have here for you, which is number 3. We've been given a wave equation. We've been given initial conditions and boundary conditions. The question simply says, determine a unique solution for this problem. And you've been given a general solution. So please attempt it. Would be curious whether you'd use the method we used in number 1 or the method we used in number 2 when it comes to substitution of the initial conditions. Boundary conditions are not a problem because they're both equal to 0. But when it comes to initial conditions, it's a different story altogether, because these two initial conditions either look like the ones that were given in number 1 or the ones given in number 2. Best wishes as you try and manipulate this problem.